Hello everyone, welcome to the final packet, nuclear chemistry. What I'll do with this one, I'll also throw on the back, show you real quick, the final lab of the semester 2. I'm just going to have you guys do nuclear chemistry worksheet number 1, okay, which I'll maybe attach, as a file on the website also, but you can get it in a normal place. All right, but only number 1, okay, not number 2, just number 1. So nuclear chemistry workshop number 1 sheet, and you can basically answer that after we've gone through this packet. Okay, so nuclear chemistry, obviously, nuclear processes, we're familiar with, nuclear radiation and things like that. There are 3 main kinds of radiation, but there are actually more. We'll talk about the different kinds as we go. But the 3 main kinds, they're all called ionizing. Basically, when they come into contact with anything, they create ions, and that's what causes bodily damage, right? So if you have ionization in your DNA, it can knock an electron off DNA or something, cause damage, cause genetic mutations, okay? So the fact that the ionization occurs is what causes the damage. If that's in your body tissues, it's serious, okay? So the ones that cause ionization are actually charged particles. So the alpha particle, and we'll look at details in a second. It's just a helium nucleus, so it has a charge of 2, so that's a charged particle, right? Then we have a beta particle, which is basically a fast-moving electron, which is a negative charge also. And then finally, we have, maybe you heard of this one, gamma, which is probably the most dangerous. That's just simply a photon, okay? But it's super, super, super high energy photon. And I like to think about gamma particles a bit, when you go to the fairground, the carnival, you have those cans sitting there in kind of like a pyramid, and you try and knock them down with a ball or something. That's like a high energy photon. So if a high energy photon gets into your body, it could knock off an electron from a molecule, a bit like, a ball in a coconut shell, right? And that's what causes the ionization. So it's removing electrons basically with a blunt force impact. And that's what causes issues. And those are very hard to stop, okay, because they pass through matter very easily. These things, as we'll see in a second, can be stopped quite easily by various barriers, but this is hard to stop. Okay, so more detail. And if you think about it, if you move a charge through space in a direction, it will be deflected by a magnetic field. So alpha particles and beta particles are deflected by a magnetic field. Gamma, which is just a photon, goes straight, no charge, right? Okay, so alpha particles, real simple, just a helium nucleus, 2 neutrons, 2 protons, okay, they're the largest radioactive particle. Beta particles, very simply speedy electrons, super fast, high energy kind of bullets, if you like. Okay, and then finally, gamma radiation is just a super high energy photon. All right, now there's 2 ways we can kind of write this down. There's the chemist way and the physics way. Okay, alpha particles, you can use the alpha symbol. That's what they do in physics. But 4 and 2, as in the mass number for chemistry with the helium nucleus. So if you remember your complete atomic symbols from back in the day, the mass number, number of protons and neutrons, number of protons down here. So you can write it either way. It's got a charge of +2, element number 2, atomic number 2, mass of 4. Okay. This can be stopped by very simple barriers, skin, thin metal foil. Okay, so if you are irradiated directly with alpha particles, it generally doesn't do you any harm. Okay, generally doesn't do you harm. We'll talk about exceptions in a second. All right, beta particles, a bit more energetic, a little smaller, a little faster. There's that kind of symbol there. So an electron is 0 mass and -1 charge. Okay, beta particle -1 charge, 0 mass. You need something a little bit thicker to stop them, plastic, thicker foil, but still, a thin barrier. Clothing basically will stop these 2 kinds of radiation. Okay, the problem came, if you think about, the one time there has been kind of a nuclear explosion, during World War II in Japan, more people died after the explosion than from the explosion because of radiation poisoning. And this one in particular, alpha particles were the main cause of radiation poisoning. But you say to yourself, well, how's that possible? Well, they get in the body through contaminated water and contaminated air and dust and things like that. So ingestion of things contaminated with these is what is the problem, okay? So, if you ever see these kind of nuclear technicians, they're not walking around in like giant kind of 2-inch thick lead shielded suits. No, they're walking around in very kind of thin, kind of almost like medical type kind of suits, because they just need to kind of stop these particles, and that it's basically a filter. So they, the particles get caught in the air filter, not so much through direct contact. Okay. The other one though, gamma, now that one is dangerous because it can penetrate probably 3 to 4 feet of concrete and then maybe 4 or 5 inches of lead. Okay. And gamma is by far the most dangerous high energy photon. It's actually just a little bit more energetic than an X-ray. Okay. And here's me, right? So gamma rays and X-rays are very close in energy. Okay, so I tend to try and avoid being scanned with X-rays. I'm that guy at the airport that refuses to get scanned because it's a kind of a chance thing. The chances of you being irradiated by an X-ray and getting kind of cancer in some form is low. But then, so smoking, right? So it's similar. I see the two things as similar. I'm just limiting my kind of exposure to radiation. So I never take an X-ray. I always get the pat down, right? I don't care. All right. So, and also, if you've ever been to like, you've had maybe a dental X-ray or something like that, you go in there and they say, oh, it's perfectly safe, and then they go and hide behind 3 feet of concrete in an adjacent room. And the next time you have an X-ray, well, why are you going to do that? Why are you standing behind 3 feet of concrete? And they say, well, I'm limiting my exposure. And I go, well, I'm being directly exposed right now. So again, it's all about risk. Okay, it's all about risk. It's all about risk management. If you go to the dentist and get an X-ray every time, that adds up, right? So be careful. All right, now. There are other forms of radiation we don't talk about, and cosmic ray, let's put that on there. Cosmic ray. That's basically a neutron. Neutrons have no charge and a mass of 1. Okay, so there's neutrons hitting the atmosphere all the time. They hit nitrogen, it eventually forms carbon-14. That's the basis of carbon dating. So neutron is a form of radiation. Okay, other ones. Positron, you may or may not know, I think you probably know, that every particle has an antiparticle, all right? So protons, antiprotons, electrons, positrons, okay? So if a nucleus, instead of emitting a beta particle, right, emits a plus electron, a positron, that's called positron emission, and that's the basis of positron emission, positron emission topography. PET scans, right? So PET scans are really cool. And if you look in the back of the packet, I think I've got a picture. We can find it. Yeah, there's a PET scan, right? So a PET scan is much better than an MRI because it shows living tissue, right? So sugar is radioactively labeled, where the positron emitter, the sugar is taken up by active cells, and cancer cells are more kind of metabolically active than regular cells, and you can see tumors and things. Okay, so the PET scanner is a very, very important kind of tool in medicine, and you can kind of irradiate all these nuclei, and they actually, some of them do positron. So fluorine, you basically substitute a fluorine 18 for a hydrogen in sugar, and you have a drink which you take, and then you glow up under a PET scanner, if that makes sense. Okay, so those are your main forms of radiation. A couple of kind of off-menu ones at the bottom there, and that's a plus electron, right? So it's an electron that's a 0 mass plus 1 charge. Okay, moving on. So now here's the thing. Why do things undergo nuclear decay? We're probably familiar with the most common form of radiation, which is kind of nuclear decay. So something like uranium will decay over time and emit particles, alpha particles, beta particles, gamma particles, or rays, right? Okay. So the big question is, well, why are heavy nuclei falling apart? And if you look in the periodic table, this is one of my pet peeves, okay? So if you look at the periodic table, everything past uranium, which is 238 down here, mass 238, element number 92, okay? Everything else past 92, they're called the post-uranic elements. So anything that's 93, 4, this is the atomic number, anything bigger than 92 is unstable. If you look at the mass number, it's all in square brackets, which means it's not a stable element, right? And that includes these guys here as well, okay? So uranium is the last stable element. Okay, that's why it's, you know, it easily falls apart, which we'll talk about more as we go. Okay, but there's plutonium, for example, right? There's americium, which is used in smoke detectors and things. Berkelium, Californium, Einsteinium, you know, they're all named after people and places, right? Okay, so up here, very simply, there are too many, and 92 is the maximum number. Any more than 92 protons in the nucleus becomes unstable. Because if you think about it, you're jamming a lot of positive charge into a very small area or volume, right? And what happens is the electrostatic repulsion of those particles basically forces the nucleus apart, makes it fall apart. Okay? And it turns out that 92 is the maximum number of protons you can have in a nucleus for it to be stable. Okay? So the post-uranic are all unstable, will fall apart to make smaller, more stable nuclei because of positive electrostatic forces inside the nucleus. And that's called the weak nuclear force. And that's responsible for nuclear decay. All right? So nuclei falling apart, nuclear decay, too many protons. Okay? Now that effect diminishes quickly after, you know, you lose a few protons. So elements actually get stable as they get lighter. This is a graph of stability essentially versus atomic number. Okay, all right. Turns out the most stable nucleus in nature, which has the perfect arrangement of protons and neutrons to make it the most stable, is iron. Okay, it's iron. Okay, so heavier things will gradually decay until they eventually form into iron. Okay, so iron is very popular. It's a very heavy element, iron, compared to others, right? Okay, but it's, you know, it's often found at the center of planets and all over the place. It's very, very abundant because it's the most stable nuclei. Okay, so when you have supernova explosions, things like that make heavier elements, iron's one of them that's generally formed. Okay, so that explains why heavy ones decay to make iron, but what about light ones? The sun fuses, so this is fission, right, splitting apart. This is fusion, sticking together. Why do light elements stick together to make heavier elements? Why are heavier elements all the way up to iron more stable? Remember, iron's the most stable. We just talked about why heavy elements fall apart to make iron. It's because of the weak nuclear force. What about light elements? Well, that's because of the strong nuclear force. And that's a hard one to explain, but when protons and neutrons get right close to each other, they stick really, really strongly. It's a very close range, very strong force. Okay, now a nice way to think about this, it's an analogy, right? So think about particles in a nucleus, a bit like, now think of a physics experiment, right? So think about two little kind of carts on a railway track, right? You've seen these carts on tracks in physics before. And then get the north pole of a magnet and the north pole of a magnet, okay? If you push these carts together, they'll eventually, as they get closer, they'll eventually repel away, won't they? That's like the weak force, right? That's like a proton repelling a proton, right? Okay, so the weak nuclear force, just think of two north poles of magnets pushing closer and closer together. Eventually, before you can touch them, they bounce away, right? But now, think about this. Let's cover these magnets with some Velcro, right? If we can push them together with just a little bit more force, they will touch. And if the Velcro's there and it touches, it engages, it sticks, right? Okay, and that's the weak nuclear force. The more particles I have in the nucleus, the more Velcro I have, right? So it's less Velcro as we go down, right? Until we get to the point where we have iron, which is the perfect balance between lots of Velcro and minimal proton-proton repulsion, and that's where iron sits in the stability. Okay, so it's like the Goldilocks zone. These are too heavy, these are too light, this is just right. Okay, so the Velcro argument and the repelling magnets, if you like, analogy. Okay, so strong versus nuclear force, strong versus weak nuclear force. This is what Einstein was famous for. Okay, and we'll get into it in more detail as we go. All right. Now, how do we write radioactive decay equations? So things that are heavy, they fall apart. How do we kind of discuss that? Well, it's kind of a very, very simple thing. If we can write a balanced chemical equation, we can write a balanced nuclear process. Okay, the very simple fact is that the mass numbers and the atomic numbers on both sides of the equation must add up to the same. Okay, so let's take some plutonium, right? So if I take plutonium, element number 94 weighs 240, right? Okay, when this falls apart, it throws out, as it's one of its decay products, and I like to write the actual chemistry, nuclei rather than alpha, but you can write alpha there if you want, right? So it forms something plus an alpha particle, right? Okay, plutonium falls apart to make something and an alpha particle. It just flies out, so the nucleus basically splits, turns into two things. Okay, now what is that other thing? Well, let's look here. So these numbers must add up. So 94 is 92 plus 2, right? What's element 92? Well, it's our friend uranium, right? Uranium's element number 92. So I can do that. Remember, that's kind of the same information. Element 92 is uranium, uranium's 92. What about the mass number here? Well, 4 plus something is 240, so 236. So it's the isotope uranium-236. All right, there we go. So we could write, you know, uranium, maybe you remember this, 236. All right, and there's a picture. There's a picture, okay? So plutonium plutonium element number 94, plutonium 240 falls apart to make uranium 236 plus an alpha particle. Okay, this undergoes fission, breaks apart to make these two things. Okay, now if you think about it, when I went over here, I lost 4 from the mass number and I lost 2 from the atomic number. So if we did a graph of, now Z is just number of protons, right? Atomic number, and N is number of neutrons. Number of neutrons went down by 2, boom, boom. Number of protons went down by 2, boom, boom. So if we see this kind of diagonal transition, right, 2 across and 2 down, that's alpha particle decay for a graph of protons versus neutrons in a nucleus. Okay, the other ones are here. As we go through, we'll kind of make sense of these, right? But if you think about it, if I simply lose a neutron emission, if I lose a beta particle, things like that. Okay, so you can rationalize these various things with these arrows. Okay, now, good point for a pause. Okay, try and write. Now remember, a beta particle is a negative charge, right? So be careful there. The charge will be -1, mass 0. The beta decay of iodine, 131, and the alpha decay of uranium, 238. Okay, try those. Pause it. Come on back. All right, so iodine. Iodine is element 53, right? And it's isotope 131. It turns into something plus an electron, beta decay, right? So -1 on the charge, 0 on the mass. So the thing it turns into has the same mass, 131. Fair enough, right? But look here, look at this, right? So what with a -1 makes 53? Well, it's 54, right? So the mass number, the protons, number of protons essentially went up. What happened in the nucleus? I turned a neutron into a proton by losing an electron, right? So element 54 is xenon. So let's look at the chart for that, right? So if I undergo beta emission, okay, the number of neutrons goes down and the number of protons goes up because I turned a neutron into a proton. It's a one diagonal shift. Okay. If you like, protons goes up. It's a +1 because I lost a -1. All right. Alpha decay, 238. Uranium 92, 238. Turns into, just for fun, we'll do the physics one, 42, all right? So it's 90, element 90, and 4 from that, 2, 3, 4. Who's 90? Element 90 is thorium. Quick story for you. Okay, when I was in undergraduate back in the 1980s, you know, the 1980s when you had less health and safety concerns in colleges, okay, we were in our 300 level inorganic class, and the final lab was the professor giving us any inorganic sample, any salt, right, any metal with any non-metal. Here's a little vial of salt. Your job is to tell me what it is. That was it, right? We had no clues, no nothing. So we were there like, oh, hell, how are we going to do this? And everyone got a different one. So I got my anion pretty quick because it was very soluble, right? Oh, okay. Might be a nitrate. And I did what's called the brown ring test for nitrates. That worked. So it's definitely a nitrate. Then I tried every single flame test, this, that, and the other. Could not find my, my metal ion. And I did remember what the guy said. He said, you can use any technique you like. And I kept him to his word, and I went up to him and I got a bit smug about it, and I said, hey, you did say any technique we like, right? And he said, yeah. And he goes, okay. I said, okay, I want you to send this to the geology department for an X-ray fluorescence spectroscopy experiment, okay? Basically, if you remember the Mars rover, how did it identify rocks on Mars, what was in them? It used this technique, right? So it's very, very expensive. It was mounted on the Mars rover, and he had to do it. He had to take the sample over there for X-ray fluorescence, and it came back thorium. Thorium. I had this stuff sitting in my pocket for a week, right? Okay, and then we were like amazed when I got it right, and my kind of fellow chemist was like, wow, let's get the Geiger counter out. We just put the Geiger counter on the sample, it just went off the scale. I'm like, that is just unbelievable. That was sitting in my pocket for a week. But luckily, it was an alpha particle emitter, right? Thorium is as well. So, you know, my skin blocked the particles, but I was not a happy camper. Okay, all right, so moving on. Nuclear transmutations, kind of like a balanced chemical equation, same concept as before. Make sure the mass and the atomic numbers kind of balance both sides, okay? So do an easy one to start, and I'll give you a few ones to try, right? So, cosmic ray, neutron capture by nitrogen-14. This is how you make carbon-14 eventually, right? So if I take nitrogen-14 in the upper atmosphere, add a neutron, zero charge, mass of 1. What does it turn into? Capture, right? So it all just kind of sticks together. The mass goes up by 1. It's still nitrogen because the atomic number didn't change, okay? All right. So that will undergo subsequent, probably if we think about it, proton emission, right? And it will turn into carbon-14, right? Okay, and that's what's, you know, that's the first step in creation of carbon-14 in the upper atmosphere. All right. Now, try this one. Pause if you want, right? Pause if you want. Try this one. Okay. All right. So neutron capture, nice and easy. Iron, you know, have a periodic table. Iron is element number 26. Atomic number 26, atomic mass 58. Neutron capture again. Mass goes up by 1. Same element. There we go. All right. Okay, got a few questions from your textbook. I'll write them out rather than you look them up. Okay, so first one, Californium. You may be asking yourself, why do these elements have names like Californium and Lawrencium, things like that? So if I look here, Americium, Californium, Berkelium, all right, Einsteinium, Fermium, Nobelium, okay, Seaborgium after Glenn Seaborg, right? Okay, these are all discovered in the 1960s at the Lawrence Livermore Laboratory in Berkeley, on the Berkeley campus, right? So it's a very famous kind of nuclear chemistry research site back in the day. And most of these kind of unstable heavy isotopes were made at the Lawrence Livermore lab back in the day. All right, so if I work at the Lawrence Livermore lab, I take Californium, which I made last week, and I bombard it with my nuclear reactor boron nuclei, right? And it makes 3 neutrons and something. What's the something? Try and figure that one out, right? Okay. Next one. So pause, give it a shot. I'll come back in a second. All right. So let's do it rather than go on. Okay, so remember these numbers out. This is 3 neutrons, right? So that's really 3, right? Because it's 3 neutrons. So 252 plus 10 is 262 minus 3, 259. So whatever it is weighs 259, right? Yeah, 259. And then down here, no charge. So that plus that is 101. Sorry, 103. I can do my math. 103. Who's number 103? Number 103 is Lawrencium, after Lawrence Livermore Laboratory. All right, there it is. Next one, this is what happens in the sun. So the sun works by fusing hydrogen and helium, right? That's what the sun does. It's a nuclear fusion reactor. Turns into regular old helium plus what? Try that one. Okay. 2 plus 3 equals 4 plus, or 1. 1 plus 2 is 2 plus 1. What has a charge of 1 and a mass of 1? A proton. Okay, if you like, plus 1. All right. Last one. Now, actually not last one, I'll do 2 more. If I do this one, hydrogen plus boron turns into 3 somethings. So the 3 somethings. So 1 plus 11 is 12, 3 of the same thing, 3 fours are 12, right? 5 and 1 is 6, 3 twos are 6. What has a mass of 4 and an atomic number of 2? Helium nuclei. There you go. All right. Now, a little bit of real life. You may have heard the term fast breeder reactor. Okay, so part of the Iran nuclear deal, which we used to have, right, was that Iran was no longer permitted to make plutonium, because plutonium makes a far better weapon than uranium, right? But it turns out that plutonium, because it's unstable, you can't dig it up. You have to make it via nuclear synthesis. And how you make plutonium is you get your regular old nuclear reactor, and around your nuclear reactor core, from which is flying out nuclear particles, like alpha particles, you put some regular old uranium-238, right? That will get bombarded by the alpha particles coming out of your regular nuclear reactor, and what will it make? Well, you tell me. 2 plus 92 is 94. 4 and that is 242. Who's that? Oh, it's plutonium. So you can make plutonium by bombarding uranium, cheap uranium actually. 235 is fissionable uranium. So the stuff they make bombs and nuclear power plants out of is uranium-235. Think about it, that makes total sense, because if it has slightly less neutrons getting in the way of those protons, they'll repel more, if you like. So nuclear, so isotope or uranium-235, it's less heavy, but it's more likely to break when it's kind of nudged, if you like. So you hit it with a proton, it falls apart. That's nuclear reactions, right? Chain nuclear reaction we'll get to later. Okay, but hey, if I take the stable form of uranium-238, which you can buy it on the internet, this is not radioactive or anything like that, and you expose it to alpha particles, it makes plutonium. I think that was an episode of Young Sheldon, but you have to check for that. All right. Now, got 1 minute left on my timer, so I'm going to pause there. When we come back, and this will be the last video of this semester, because we'll finish up this packet and we'll talk about your homework, your lab a little bit. Okay. When we come back, we'll talk about the mathematics behind nuclear decay. Turns out that all nuclear decay processes, if we think about it, it's what we call a unimolecular process, just one thing falling apart. So it's always first order. So we know the math already. We'll just change the symbols so to match the physicists, and you know, it's just first order kinetics. So if you want to kind of flip back and look at your kinetics, it's the same as first order, so we can use all that math directly. Okay, so stop there, and I'll see you in a little bit.